Welcome to Year 8 Physics. This particular topic in physics is energy, so it's an introduction to energy. In Year 7 you would have looked at forces and simple machines. We're just going that little bit further. You can see there's a lot of energy going on in this picture. There's a 38 metre drop. It's called the Gap. It's in Albany, Western Australia, and when there's really big swell it comes in, and we can see the swell has almost got to the top from where the ocean level is down here. So we've got a lot of kinetic energy going on. A lot of wind, a lot of swell. So kinetic energy is energy of moving things. In this picture we can see heat energy is actually a bit of a, must be back burning going on over there. We can see that the sun's probably over to the left a little bit. So there's light and heat energy there. This is a wind turbine at the Albany wind farm. This turbine will turn, so it will gain kinetic energy that it's gained from the wind. And the wind has kinetic energy as well. So it transfers that energy to the turbine, which then produces electrical energy. Here's the curriculum outcomes. So really we're just looking at types of energy, including kinetic, heat and potential. I'll tell you some interesting things about basically all energy is either kinetic or potential. So that's an interesting concept, but we'll break them up into different sorts. Looking at energy transformations and transfers. So how does one energy type become another? Or at least acknowledging that one energy type becomes another, and looking at the fact that, like with the wind turbine, we can transfer kinetic energy from the wind to the turbine itself. And then we can transform it into electrical energy. If you want to read these, the link is in the description. Where we're going to start, we're going to look at forms of energy, transfer and transformation. We'll look at energy efficiency, and then just have a particular look at sound and light. Sound and light leads into a little bit into Year 9 physics. Certainly stuff that you'd look at if you did Year 11 physics. So it's just a bit of an introduction to that sort of stuff. So we can see that energy is what makes matter move or change. We can see kinetic energy and potential energy over this side. So all of these things down here are types of kinetic energy because they're energy that comes from movement. Potential energy, all of these things down here are considered potential energy. And we'll look at each of those ones in a little bit more detail as we go. So a pretty simple definition of energy is that it's the capacity to do work. So something that can do work is considered to be energy, or requires energy in order for work to be done. So objects or organisms can perform tasks, and by performing tasks they're technically doing work, and they can do that if they have a source of energy. So the ones we're really going to look at here: kinetic, heat, light energy, sound energy, electrical energy. Just at the start, we will get to potential energy later. Kinetic energy is the energy of anything that is moving. Things that are more obvious to us is objects or organisms that are moving. So this car is moving, these skydivers are falling, so they're moving. This bird, this eagle, is moving. We can see that. And we can actually work out how much energy something contains if we know its mass and we know v, so that's its velocity. So if we know its mass and how fast it's moving, we actually know how much kinetic energy it has. So we could work it out for this car, and we're just going to do that for another car. I'm sure that car's heavier than 800 kilos. So we've got a car with passengers, has a mass of 800 kilograms, and is traveling at 30 meters per second. Now we notice the units are kilograms and meters per second, and that's important. What is the kinetic energy of the vehicle? So we've got the equation E equals, so the K means kinetic, E kinetic equals half mv squared. E kinetic equals the half stays there. The mass is 800, so we put 800 there because it's in kilograms. If this was in grams, we would need to convert it into kilograms. So this would be 800,000 grams, and then we'd make it 800 kilograms. That would be a bit annoying, but that happens sometimes when you're doing questions. And in Year 10 it certainly will. And the velocity is 30 meters per second. If you get a velocity in kilometers per hour, you would need to convert it. But at Year 8 level, nobody's going to be that mean to you. You probably aren't even going to get assessed on using this sort of equation. But it's good to see it. It's good to know. In Year 10 you definitely will be. And there will be lots of annoying tricks that people put into the questions for you have to do. What half times 800 times 30 squared? 30 squared is 900. So 1/2 times 800 times 900 is 360,000, but it's in joules. And you've probably heard of, you may have heard of a joule, but you've certainly heard of a kilojoule. Kilo means 1,000. So if we divide this number by 1,000, we get down to 360 and kilojoules. Because there's the K there, we know that's 1,000 joules. So 360,000 joules, and that's the same as what we've got up here. It's just a more convenient way to write it. Heat energy can change the temperature of something or change its physical state. Righty, so if you apply heat energy to something that's 5 degrees, you might get it to 10 degrees Celsius. Or if you apply heat to a solid, you might get it to become a liquid. If you apply heat to that liquid, you might get it to become a gas, and that's what it means by changing physical state. We can get heat energy from things like stars, friction, chemical reactions, probably not the only things, but some of the main things. And heat energy can be transferred through 3 main methods, or actually 3 only methods. Conduction, so heat moves through solids from one end to the other. We've got a solid, we've got one end is heated and it conducts along to the handle. You know how the handle gets hot of a pot if it's metal? That's why we often have rubber or plastic around the handle of a pot. You need to be careful if it's metal all the way. Conduction, so it's a movement of heat through a solid, is called conduction. Occasionally you can get conduction, really minor conduction in a liquid, but it's not really worth talking about. Convection, so this is heat transferred by a moving liquid or gas. So the wind is an example of convection. It can happen in a liquid or a gas. So you'll notice when you put the pot on a stove, it all starts moving around. So the heat is being moved from the bottom to the top, and then it's sort of going all the way around inside that pot. So that's called convection when we get a liquid or a gas, moving around, transferring heat around. The other one is radiation. So we get waves of heat moving from a hot object. So light is an example of this. You've seen hot coals in a fireplace and you feel that burning that comes from them. Now you're not touching them, so it's not conduction. It's not the air in between you. There's probably a little bit of convection, but usually the air is going to go straight up for fire. And the air won't actually hit you, but you can still feel the radiant heat from it. Now the interesting thing about radiant heat is it can travel through a vacuum, so there doesn't need to be a medium. It doesn't need to be a solid, liquid or gas there for radiant heat to come to you. So it's a kind of light. It's infrared light. Specific heat capacity, again, this is good to have a look at, but you might have some tasks on it, but if it's in a test, it's going to be a really simple question. That's quite straightforward. So what the specific heat capacity of substance is it's the energy required to raise a substance, so a liquid or a solid, by a temperature change of 1 degree Celsius. We're not including gas in this. That's a whole other ballgame, but we're just going to worry about this one. So the specific heat capacity equals the mass, because mass would have a difference to do with how much you can change it, times the specific heat. So that is different from that. That's the specific heat capacity. That's the specific heat. Delta means change. So this little triangle, we call it delta, and it means change. Change in temperature. Mass times the specific heat times the change in temperature. So Q's energy in joules, M's in kilograms, C has really crazy units like that, don't worry too much about that, and delta T is the temperature change. Now, technically it's supposed to be in something called Kelvin, but it works with degrees Celsius because they're the same size, so let's not worry too much. So water has a specific heat of 4,180 joules. So it takes 4,180 joules to raise the temperature of water by 1 degree Celsius per milliliter. That's a lot of energy, isn't it? 4.1 kilojoules to raise the temperature of 1 ml of water by 1 degree Celsius. Water has a really high specific heat compared to other things. For instance, pretty sure copper is less than 1,000. So 4 times as much energy. That's why water is used in radiators in cars. Okay, how much heat, so Q, is needed for 3.75 kilograms of water to rise in temperature by 25 degrees Celsius? So we have M, the mass, 375, the specific heat of water, 4,180, and the change in temperature, we're going to change it by 25 degrees. So it doesn't matter if it's going from 25 to 50, from 50 to 75, 10 to 35, and it's got, so 25 degrees is 25 Kelvin. That should have a C there for Celsius. Anyway, so here's our equation. Substitute mass in, substitute specific heat in, substitute change in temperature in, and we end up getting 391,000 joules or 392 kilojoules. We can pause that and have a closer look if you'd like to. Light energy, it's often associated with heat energy. It's hard to get light without heat. You're always, well, it's impossible to get light without heat. Anyway, it comes from anything that's luminescent. Now, luminescent means it emits its own light. You'd remember from year 7 that the moon is not, well, it's not luminescent. The light you see from the moon is reflected from the sun. It is luminescent. It's above minus 273 degrees Celsius, which is the temperature at which something does not emit any heat. And heat is a form of light. Now, we can't see it with our eyes, so we kind of just consider stuff in the light spectrum that we can sort of see with our eyes. So if you're in a dark room and all the lights are out, if you can't see it, it's not emitting light, even though it still has some heat. Light travels in waves and it can be reflected. So we have a sunset in Carnarvon. I thought it was a pretty cool one. And we have a port up at Wyndham and the Milky Way. Lots of stars in there. It's a galaxy. Sound energy. So sound energy is caused by vibrations of particles in a medium like solids, liquids and gases. So for sound to transfer, you need a medium. So the old joke about in space no one can hear you scream, it's true. Because there's no particles, well, essentially no particles, in order for the energy to transfer from your vocal cords to whoever's listening. Sound travels in waves also, but they're different kind of waves. So the waves light travels in. And this is a bit about the vacuum. So I've got this little fella here. Why do you think I'd have a bat to do with sound waves? Have a think about that while we look at this. So we've got a vibrating speaker and we've got compressions of particles and rarefactions or extensions of particles. So not much there, not much there. So this is what sound waves look like if we could see the particles themselves. It takes a little bit of time for sound to get to you. You'd notice that if somebody's running 100 meters and they're at start line and you hear the beeper or the gun or something like that, you notice that you see the smoke before you hear the bang. Lightnings are similar, so you'll see the light before you'll hear the noise of the lightning. So light travels almost instantaneous, but not quite. Very fast. On Earth, yeah, pretty much instantaneous. There is a slight delay, but it's a time that is irrelevant. But certainly sound, so it travels about 330 meters a second. That's why when you hear or when you see a lightning strike or a lightning flash, you count, and if you get 6 seconds, you know it's 2 kilometers away. If you get 3 seconds, you know it's 1 kilometer away. If you get less than that, you know it's pretty close. So electrical energy is the flow of charged particles, like electrons, doesn't always have to be electrons, but generally speaking it's electrons, through a medium like metal or air. So we've got these electrons going through air. A couple of lightning strikes at the same time. That's pretty cool. That's from the Pilbara. This is a Pilbara as well. So we've got some electrical. So we can pump electrons along these wires so that energy will do work when it gets to your home or it gets to a factory or street lights or wherever it's going. And this is electrical energy producing heat and light energy. The thing about electrical energy, we can store it in batteries as chemical potential energy. Sometimes we can store it in a battery as gravitational potential energy. You might have learnt in Year 7 resources, damming water to store energy and then pumping it through turbines downhill creates electrical energy. That's another way of storing electrical energy, storing it as gravitational potential energy. Let's go back to the bat. Echolocation. That's how they use sound energy. At night time when they can't see where they're going, they use echolocation to see where they're going, but they see using their ears.